In the vast cosmic darkness, there exists a place where space and time break down completely, where the laws of physics crumble and reality itself bends beyond recognition. We call this monster a black hole. But what if everything you know, everything you see, the entire observable universe around you, is actually trapped inside one of these cosmic prisons? Recent discoveries from the James Webb Space Telescope have shaken astronomy to its core, revealing patterns that shouldn't exist if our universe were truly random. Prepare yourselves for a journey that will challenge everything you thought you knew about reality. We begin. Imagine falling through a doorway that seals shut behind you forever. This is the reality of a black hole's event horizon, a boundary in space where escape becomes impossible, where even light itself becomes trapped in an eternal dance toward destruction. The event horizon marks the point of no return, a spherical shell of doom surrounding the most extreme objects in our universe. But here's what makes your mind reel. The size of this cosmic prison depends entirely on how much matter feeds it. Double the mass, and you double the diameter. 10 times the mass creates a black hole, 10 times larger. This isn't just theoretical mathematics. It's a linear relationship that holds true throughout the cosmos. From stellar mass black holes to the supermassive monsters lurking at galactic centers. Now comes the truly mind-bending calculation. When astrophysicists take the total mass of our observable universe and ask a simple question, how large would a black hole containing this much matter be? The answer stops them cold. The event horizon would stretch across roughly 93 billion light years, matching almost perfectly with the size of our cosmic horizon, the farthest distance from which light has had time to reach us since the universe began. This isn't just a curious coincidence. The average density of matter within our cosmic horizon matches exactly what you'd expect to find inside a black hole of this enormous size. It's as if someone took our entire universe and compressed it to the precise density required for gravitational collapse. Yet somehow we exist comfortably within this cosmic prison without even knowing it. The mathematics become even more intriguing when you consider what Einstein's general relativity predicts happens inside a black hole. Rather than ending in destruction, the equations suggest that a completely new space-time opens up on the other side of collapse. If you could somehow survive the journey through a black hole, you would witness the entire future history of the universe you left behind unfolding in fast forward, while ahead of you, an entirely new cosmos begins to expand and evolve. This raises the most profound question in modern cosmology. Could we be living in that new universe that opened up? Are we the product of some ancient cosmic collapse that occurred in a parent universe we can never observe or contact? Our universe shows remarkable signs of having specific initial conditions, precise values for fundamental constants, a particular geometry, and now evidence suggesting it might even have inherited angular momentum from its parent. The implications stretch far beyond academic curiosity. If our universe truly exists within a black hole, then every black hole in our cosmos could harbor its own baby universe, completely isolated from us by the one-way nature of the event horizon. Entire civilizations, countless worlds, infinite possibilities could exist beyond those dark boundaries, forever hidden from our observation, but nevertheless real and thriving in their own pocket dimensions of reality. The story of how we discovered our cosmic prison begins with a brilliant physicist named Roger Penrose and his mathematical proof that seemed to seal our fate. In 1965, Penrose demonstrated that under very general conditions, gravitational collapse must inevitably lead to a singularity, a point where matter crushes itself into infinite density, and the laws of physics simply give up and walk away. This singularity theorem became the foundation for our understanding of black holes, extended later by Stephen Hawking and others to show that these mathematical monsters are not just possible, but unavoidable in our universe. For decades, scientists accepted that anything falling into a black hole would be compressed beyond recognition, crushed into a point of zero volume, where time ends and space loses all meaning. But Penrose's theorem relied on classical physics, the familiar world of everyday objects and predictable forces. When quantum mechanics enters the picture, everything changes. At the subatomic level, particles refuse to follow classical rules, exhibiting behaviors that seem impossible in our everyday experience. The quantum world operates on fundamentally different principles, including something called the exclusion principle. This principle states that no two identical particles can occupy the same quantum state. Think of it as nature's ultimate traffic law. Particles with the same properties simply cannot squeeze into the same space, no matter how much pressure you apply. As matter collapses toward a black hole's center, this quantum traffic jam becomes critically important. Recent calculations by researchers at the University of Portsmouth reveal something extraordinary. When quantum effects are properly included in the mathematics of gravitational collapse, the inevitable singularity disappears. Instead of crushing matter into nothingness, the collapse reaches a maximum density and then bounces back, like a cosmic rubber ball hitting an invisible wall and rebounding with tremendous force. This bounce doesn't require exotic physics or mysterious new particles. It emerges naturally from combining Einstein's general relativity with basic quantum mechanics, two theories we already know and trust. The mathematics show that as collapsing matter approaches the potential singularity, quantum pressure builds up until it overcomes gravity itself, forcing the collapse to reverse direction. What emerges from this cosmic rebound is remarkable. A new expanding universe with properties that closely match our own observable cosmos. The bounce naturally produces two phases of accelerated expansion that mirror both cosmic inflation in the early universe and the mysterious dark energy driving current acceleration. No hypothetical fields or speculative physics required, just the inevitable consequence of quantum mechanics preventing infinite compression. This means our Big Bang might not have been the beginning of everything, but rather the moment of maximum compression, followed by explosive expansion in a cosmic cycle that could repeat endlessly. We exist not at the start of time, but potentially in the middle of an eternal dance between collapse and expansion, between ending and beginning. The universe that collapsed to create our cosmos left its fingerprints everywhere, in the precise values of physical constants, in the geometry of space itself, and possibly in the very direction that galaxies spin throughout the observable universe. Deep in the heart of Kansas State University, computer scientist Lior Shkimir was about to make a discovery that would shake the foundations of cosmology. Using images from the James Webb Space Telescope's Advanced Deep Extragalactic Survey, he was examining something that should have been utterly random: the direction that spiral galaxies rotate as seen from Earth. In a truly random universe, you would expect roughly half of all galaxies to spin clockwise and half to spin counterclockwise, like flipping coins across cosmic distances. The slight variations you might see would be nothing more than statistical noise, meaningless fluctuations that average out over large samples. But when Shkimir analyzed 263 galaxies from the deep universe, he found something that shouldn't exist. 60% of the galaxies rotated clockwise. Only 40% spun counterclockwise. The probability of this happening by pure chance was less than 700%. Astronomically unlikely in a universe governed by randomness. Something was creating a preferred direction of rotation on the largest scales imaginable, violating our most basic assumptions about cosmic symmetry. This discovery wasn't entirely unexpected. Previous observations using ground-based telescopes had hinted at similar asymmetries, but the James Webb Space Telescope's unprecedented ability to peer into the deep universe revealed the pattern with startling clarity. Even more intriguingly, the asymmetry appeared to grow stronger when looking at more distant galaxies, objects we see as they existed billions of years ago when the universe was young. The pattern showed another curious feature. The asymmetry peaked near the galactic poles, but the direction's perpendicular to our Milky Way's disk. This suggested that whatever was causing the preferred rotation had a specific relationship to our own galaxy's orientation in space, as if there existed some cosmic axis running through the universe that influenced how galaxies form and evolve. Shkimir used an automated computer program called Gandalizer to classify each galaxy's rotation direction, eliminating human bias from the analysis. The program converts galaxy images into radial intensity plots, detecting how spiral arms curve to determine rotation direction. This objective, reproducible method revealed the cosmic asymmetry with mathematical precision that anyone could verify. The implications were staggering. If galaxies truly preferred one rotation direction over another, it meant the universe was not isotropic. It didn't look the same in all directions. This violated the cosmological principle, one of the fundamental assumptions underlying our understanding of cosmic evolution. The universe had to have some kind of built-in asymmetry, some preferred axis or direction that influenced the formation and rotation of galaxies across billions of light years. But what could create such a massive scale preference? In our everyday experience, objects rotate because some force set them spinning. We see this in everything from ice skaters pulling in their arms to gas clouds collapsing under gravity. The conservation of angular momentum ensures that any initial rotation gets amplified as objects shrink. But it doesn't explain why the universe itself might have a preferred spin direction. The answer might lie in the most extreme objects known to physics. Black holes that rotate with incredible speed and possess the power to influence space and time itself across vast distances. Every black hole in the universe spins. This isn't speculation or theory. It's an observational fact carved into the fabric of space, time itself. When massive stars collapse to form black holes, they inherit the rotation of their parent stars and amplify it to incredible extremes. The conservation of angular momentum transforms a slowly rotating stellar giant into a cosmic hurricane of warped space, time, spinning so fast it drags space and time around with it. But here's where the story becomes truly mind-bending. According to black hole physics, only two pieces of information can pass through the event horizon from the outside universe: total mass and angular momentum. Everything else, chemical composition, temperature, magnetic fields, even the complex history of how the matter formed gets erased. The black hole becomes a simple object defined entirely by how much it weighs and how fast it spins. If our universe truly exists inside a black hole, then it must have inherited the angular momentum of whatever collapsed to create it. This inherited spin would manifest as a cosmic axis, a preferred direction woven into the very fabric of space, time that influences how matter moves and galaxies form throughout our observable cosmos. Think of it like cosmic DNA. Just as living organisms inherit traits from their parents, our universe would carry the rotational signature of its parent black hole. This inheritance wouldn't be visible in everyday phenomena. The effect would be far too subtle to notice in local physics. But across cosmic distances and billions of years of evolution, this inherited spin could accumulate into the galaxy rotation asymmetry that James Webb detected. Theoretical physicist Nikodem Poplawski of the University of New Haven has championed this idea for years. In his model, when matter falls into a black hole, it doesn't get crushed into a singularity. Instead, quantum effects prevent infinite compression, causing the matter to bounce and expand into a new universe on the other side of the event horizon. This new cosmos appears isolated from its parent, connected only through the warped geometry of space, time itself. The parent universe would appear to us as a white hole, the theoretical opposite of a black hole that cannot be entered from outside, and instead ejects matter and energy. But we could never observe this white hole because it would exist beyond our cosmic horizon in regions of space, time that light from our universe can never reach. This creates a stunning picture of cosmic evolution. Every black hole in our universe could be the birthplace of a new cosmos, spawning baby universes that inherit the angular momentum and basic properties of their parents. These universes would be completely isolated from us, developing their own galaxies, stars, planets, and potentially life, all while remaining forever hidden behind the one-way barrier of the event horizon. The asymmetry in galaxy rotation becomes a fossil record of our cosmic birth, preserved across 13.8 billion years of universal evolution. It's the signature of our parent black hole, written in the very spin of galaxies across the observable universe, waiting billions of years for creatures like us to develop telescopes powerful enough to read this ancient cosmic message. When the James Webb Space Telescope opened its golden eyes to the universe in 2022, it wasn't just another advance in astronomical technology. It was a complete revolution in how we observe cosmic history. This $10 billion marvel compared deeper into space and further back in time than any instrument humanity has ever built, revealing the universe as it existed when it was young, wild, and dramatically different from today. The telescope's unprecedented infrared vision allows it to see through cosmic dust and detect the light from the very first galaxies that formed after the Big Bang. But James Webb's true power lies in its ability to capture fine details across vast cosmic distances, revealing the intricate structure and motion of galaxies that existed billions of years ago with clarity that would have been impossible just decades earlier. This revolutionary capability enabled Schemia's discovery of the galaxy rotation asymmetry. Previous ground-based surveys had hinted at similar patterns, but they lacked the resolution and depth needed to make definitive measurements. James Webb changed everything by providing crystal clear images of hundreds of distant galaxies, each one a snapshot of cosmic conditions from the universe's early epochs. The Advanced Deep Extragalactic Survey, or JADES, represents one of the largest and most comprehensive deep field imaging programs ever undertaken. By focusing on well-studied regions like the Great Observatory's Origins Deep Survey fields, JADES builds upon decades of previous observations while pushing the boundaries of what we can detect and measure in the distant universe. What makes these observations so powerful is their objectivity. Schemia's team used automated computer algorithms to analyze galaxy shapes and determine rotation directions, eliminating human bias that could skew results. The GALI-CSE program converts each galaxy image into mathematical data, detecting spiral arm patterns and classifying rotation with reproducible precision that any researcher can verify. The results were undeniable. Galaxy after galaxy showed the same preference for clockwise rotation when viewed from Earth. The pattern wasn't subtle or marginal. It was a clear, statistically significant deviation from randomness that demanded explanation. Even more remarkably, the asymmetry appeared stronger in more distant galaxies, suggesting that whatever causes this cosmic preference was more pronounced in the early universe. James Webb's observations revealed another crucial detail. The rotation asymmetry peaked near the galactic poles, with different patterns at the northern and southern poles relative to our Milky Way. This suggested that the effect wasn't just random cosmic structure, but had a specific geometric relationship to our position and orientation in the universe. These discoveries represent just the beginning of James Webb's contributions to cosmology. The telescope continues to observe the deep universe, building larger samples of distant galaxies, and potentially confirming whether the rotation asymmetry represents a fundamental feature of cosmic structure or results from more mundane observational effects. If confirmed by additional observations, the James Webb Galaxy rotation discovery could force astronomers to completely rethink their understanding of cosmic evolution the nature of space-time, and our place within what might be the most elaborate cosmic prison ever conceived. A universe trapped forever inside the event horizon of an unimaginably massive black hole. The mathematics that describe our potential cosmic prison are both elegant and terrifying in their implications. When Einstein developed his field equations for general relativity, he created a mathematical framework that could describe the most extreme objects in the universe, including black holes so massive they could contain entire cosmos within their event horizons. The key insight comes from understanding how black holes scale with mass. Unlike everyday objects, where doubling the mass might double the weight, but only slightly increase the size, black holes follow a linear relationship between mass and radius. This means a black hole with twice the mass has exactly twice the diameter. 10 times the mass creates an event horizon 10 times larger. This scaling continues indefinitely, with no upper limit on how large a black hole can theoretically become. When cosmologists perform the calculation for our entire observable universe, taking every galaxy, star, planet, and particle within our cosmic horizon, and asking how large a black hole would need to be to contain this much mass, the answer is shocking in its precision. The resulting event horizon would measure approximately 93 billion light years across, almost exactly matching the size of our observable universe. But the match goes deeper than just size. The average density of matter within our cosmic horizon equals approximately 10 to the negative 27th kilograms per cubic meter. This incredibly low density, far lower than the best vacuum we can create in laboratories, matches precisely what general relativity predicts for the interior of a black hole with our universe's mass and size. This density match isn't approximate or close, it's exact within our current measurement uncertainties. It's as if our universe was designed to fit perfectly within the event horizon of a cosmic black hole, with every parameter tuned to enable this extraordinary coincidence. Either we're witnessing the most remarkable accident in cosmic history, or our universe truly exists within such a gravitational prison. The mathematics become even more compelling when you include rotation. If our universe inherited angular momentum from a parent black hole, this would create what physicists call a curved black hole, a rotating solution to Einstein's equations that drag space-time around with it. The rotation would establish a cosmic axis, a preferred direction that could influence how matter moves and galaxies form across billions of years of cosmic evolution. Recent calculations by researchers at the University of Portsmouth show that quantum mechanics prevents the infinite compression that classical physics predicts at black hole centers. Instead of forming a singularity, collapsing matter reaches maximum density and then bounces, expanding into a new universe with properties that remarkably match our observed cosmos. This quantum bounce creates two distinct phases of accelerated expansion, one corresponding to cosmic inflation in the early universe, and another matching the dark energy that currently drives universal expansion. Both emerged naturally from the mathematics, without requiring hypothetical particles or mysterious energy fields. The equations suggest our Big Bang wasn't the beginning of time, but rather the moment when quantum pressure overcame gravitational collapse, transforming destruction into creation and giving birth to our expanding cosmos within the protective boundaries of a cosmic event horizon that we can never see or escape. We live within multiple horizons, each one of boundary beyond which certain types of information can never reach us. The most familiar is our cosmic horizon. The distance light has traveled since the Big Bang, creating a sphere around Earth beyond which we can observe nothing. But if we exist inside a black hole, we face an even more fundamental boundary, the event horizon that separates our universe from the parent cosmos that created us. This creates a profound paradox in our understanding of cosmic evolution. Traditional cosmology assumes our universe is open and infinite, expanding into empty space with no barriers to constrain its growth. But if we exist within a black hole, our entire cosmos is enclosed within a finite boundary that we can never observe across. We're like prisoners in the ultimate cosmic jail, completely unaware of our confinement. The event horizon that contains us operates according to the strangest rules in physics. Information can flow inward across this boundary, but never outward. This means our universe could receive matter and energy from the parent cosmos, but nothing we create or discover can ever escape to influence the larger reality beyond our cosmic prison. From the perspective of observers in the parent universe, our entire cosmic history would unfold in an instant. Time dilation near the event horizon would cause our billions of years of evolution to compress into moments as seen from outside. Stars would be born, live their entire lives, and die in what appears to outside observers as a brief flash of light before disappearing forever behind the horizon. But from our internal perspective, time flows normally. We experience the full richness of cosmic evolution, galaxies forming, stars igniting, planets developing life, and civilizations arising to contemplate their place in the universe. The horizon that imprisons us remains forever invisible, always beyond our ability to detect or measure directly. This imprisonment isn't just theoretical. If our universe exists within a black hole, then every black hole we observe in our cosmos could contain its own universe, complete with galaxies, stars, and potentially intelligent life. These nested universes would be completely isolated from us and from each other, creating an infinite hierarchy of cosmic realities. The James Webb Space Telescope's discovery of galaxy rotation asymmetry might be our first direct evidence of this cosmic imprisonment. The preferred rotation direction could be the signature of our parent black hole, written into the fabric of space-time itself and preserved across billions of years of cosmic evolution. It's like finding a cosmic fingerprint that reveals our true origin. But this raises disturbing questions about the nature of reality. If we can never escape our cosmic prison, if we can never communicate with or observe the parent universe that created us, does it even matter whether we exist inside a black hole? Our physics, our chemistry, our biology all work exactly as we observe them. The stars still shine, planets still orbit, life still evolves. Perhaps the most profound implication is that our universe might be just one of countless cosmic bubbles, each one containing its own version of physics, its own galaxies, its own potential for life and intelligence, all sealed away from each other by the fundamental laws that govern black holes and the flow of information across event horizons. At the heart of black hole cosmology lies one of the most mind-bending concepts in theoretical physics, the white hole. If black holes are cosmic vacuum cleaners that suck everything inward past a point of no return, then white holes are their exact opposite. Cosmic fountains that spew matter and energy outward with such violence that nothing can ever enter them from outside. Einstein's equations are mathematically symmetric, meaning that for every black hole solution that describes matter flowing inward, there exists a corresponding white hole solution where everything flows outward. While we've never observed a white hole in our universe, they represent a crucial piece of the cosmic puzzle if our reality truly exists within a black hole. According to the black hole universe theory, the Big Bang wasn't an explosion from nothing. It was our first glimpse of a white hole. The white hole represents the other side of the parent black hole that gave birth to our cosmos. All the matter and energy that fell into the parent black hole eventually emerged through this white hole connection, expanding to create the galaxies, stars, and planets we observe today. This creates a stunning picture of cosmic recycling. Matter from the parent universe collapsed through a black hole, traveled through a region of warped space-time, where the normal rules of physics break down, and then exploded outward through a white hole to begin our universal expansion. The white hole becomes the source of our cosmic horizon, the place from which all matter and energy in our universe ultimately originated. But here's the crucial detail: we can never observe this white hole directly. It exists beyond our cosmic horizon, in a region of space-time that light from our universe can never reach. The white hole appears to us as the distant past, the moment of cosmic origin that we can approach but never quite touch through our observations. The white hole connection explains several mysterious features of our universe. It accounts for why the cosmic microwave background, the afterglow of the Big Bang, appears so uniform across the sky. This radiation represents the last light from the white hole region, stretched and cooled by billions of years of cosmic expansion, but still carrying the signature of our cosmic birth. It also explains the arrow of time. White time flows forward rather than backward in our universe. The white hole establishes a preferred direction for the flow of causality, inherited from the parent black hole's interior geometry. Time flows from the white hole region toward our current cosmic era, creating the temporal asymmetry that allows for the evolution of complexity, life, and consciousness. Recent mathematical work suggests that white holes might not be completely hypothetical. Quantum effects at the center of black holes could create the conditions necessary for white hole formation, turning what appears to be cosmic destruction into cosmic creation. The bounce that prevents gravitational singularities could manifest as a white hole explosion, launching new universes from the hearts of dying black holes. This means our cosmic origin story is actually a tale of death and rebirth, where the gravitational collapse that created our parent black hole became the creative force that launched our expanding universe through its white hole connection. If our universe exists inside a black hole, then every black hole we observe in our cosmos becomes a doorway to another reality. This creates an infinite hierarchy of nested universes, each one sealed away from the others by the one-way nature of event horizons, yet all connected through the fundamental geometry of space, time itself. Consider the supermassive black hole at the center of our Milky Way galaxy. This gravitational monster contains over 4 million times the mass of our Sun, compressed into a region smaller than our solar system. According to black hole cosmology, this object doesn't just bend light into the distort space. It harbors an entire universe within its event horizon, complete with its own galaxies, stars, planets, and potentially intelligent civilizations. The beings living in that universe would have no knowledge of our existence. Their cosmos would appear infinite and expanding, just as ours does to us. They would develop their own physics, discover their own cosmic microwave background, and eventually build telescopes to explore their deep universe. They might even discover galaxy rotation asymmetries that lead them to suspect they exist within a black hole, just as we're beginning to suspect about our own reality. But the hierarchy doesn't stop there. Every black hole in their universe would contain another nested cosmos, and every black hole in those universes would spawn yet another level of reality. This process continues infinitely in both directions. We exist within larger universes that themselves exist within even larger ones, while simultaneously containing smaller universes within our own black holes. The scale of this cosmic nesting is absolutely staggering. Our observable universe contains an estimated 100 billion galaxies, and each galaxy harbors millions to billions of black holes. If each black hole contains its own universe, then our cosmos alone gives birth to more universes than there are stars in our galaxy, and each of those universes spawns its own infinite hierarchy of nested realities. This creates what physicists call a cosmic multiverse, but not the kind usually discussed in popular science. Instead of parallel universes existing alongside ours in higher dimensions, these nested universes exist within the three-dimensional space we already know, separated only by the event horizons that make communication impossible. The implications for life and intelligence are profound. If black holes naturally create conditions suitable for universe formation, and if universes naturally evolve to produce life, then consciousness might be far more common than we ever imagined. Every black hole becomes a potential nursery for billions of years of cosmic evolution, stellar formation, planetary development, and biological complexity. Yet all these civilizations remain forever isolated from each other. The event horizons that separate nested universes are absolute barriers to communication and travel. No signal, no matter how powerful, can cross from one universe to another. No technology, no matter how advanced, can breach the one-way barrier that seals each cosmos within its gravitational present. We might share our galaxy with billions of nested universes, each one teeming with life and intelligence, yet we'll never know they exist. and they'll never know about us. The cosmic hierarchy ensures that each universe evolves in complete isolation, developing its own unique version of physics, chemistry, biology, and perhaps consciousness itself. As we reach the end of our journey through the possibility that our universe exists within a black hole, the evidence forms a compelling but incomplete picture. Like cosmic detectives, we've gathered clues that point toward an extraordinary conclusion, yet definitive proof remains tantalizingly beyond our reach. The first clue lies in the remarkable size and density match between our observable universe and what physics predicts for the interior of a massive black hole. This isn't just a rough approximation. The numbers align with shocking precision, as if our cosmos was designed to fit perfectly within a gravitational prison of cosmic proportions. The second clue comes from the James Webb Space Telescope's discovery of galaxy rotation asymmetry. The fact that galaxies prefer one rotation direction over another violates our basic assumptions about cosmic randomness and suggests our universe inherited angular momentum from some external source, exactly what black hole cosmology predicts. The third clue emerges from quantum mechanics and its ability to prevent the infinite compression that classical physics demands at black hole centers. The quantum bounce that replaces gravitational singularities provides a natural mechanism for universe creation, transforming cosmic death into cosmic birth through the fundamental laws we already understand. But perhaps the most intriguing clue comes from the problems that black hole cosmology solves. It explains the mysterious uniformity of the cosmic microwave background, the precise values of fundamental constants that allow complexity to emerge, and the two distinct phases of cosmic acceleration without requiring exotic particles or speculative physics. However, significant challenges remain. The galaxy rotation asymmetry could result from observational biases rather than fundamental cosmic structure. Our measurements of universal expansion and age could be systematically incorrect, leading us to see patterns that don't reflect true cosmic properties. The mathematical elegance of black hole cosmology doesn't guarantee its physical reality. The ultimate test will come from additional observations. If more galaxies observed by James Webb and future telescopes confirm the rotation asymmetry, if the pattern becomes stronger at greater distances, as black hole cosmology predicts, then we'll have powerful evidence for our cosmic imprisonment. If the asymmetry disappears with better data or more careful analysis, we'll need to search for other explanations. But perhaps the most profound implication isn't whether we exist inside a black hole, but what this possibility reveals about the nature of reality itself. If our universe can exist within a gravitational prison without us ever knowing it, if physics works identically, whether we're free or trapped, then what does it mean to be imprisoned by forces we cannot observe or escape? The search for our cosmic origin continues, driven by humanity's relentless curiosity about our place in the grand scheme of existence. Whether we live in an open, infinite universe or within the event horizon of an unimaginably massive black hole, we remain the same conscious beings capable of contemplating our own cosmic circumstances. the universe keeps its deepest secrets well hidden, revealing them only to those brave enough to question everything they think they know about reality. In our quest to understand whether we exist within a cosmic prison, we've discovered that the true mystery isn't where we are, but how consciousness emerged to ask these questions in the first place. But wait, there's another explanation for the galaxy rotation mystery that could shatter our cosmic prison theory entirely. What if the James Webb Space Telescope isn't revealing fundamental cosmic structure, but instead detecting a subtle bias in how we observe the universe from our moving platform within the Milky Way galaxy? Our solar system races through space at incredible speeds. We orbit the galactic center at over 200 kilometers per second, carrying Earth on a cosmic carousel that never stops spinning. This motion creates what physicists call the Doppler effect, the same phenomenon that makes an ambulance siren change pitch as it passes by, except applied to light waves traveling across billions of years and countless light years of space. When galaxies rotate in the same direction as our Milky Way's motion, their light gets shifted toward the blue end of the spectrum, making them appear slightly brighter and easier to detect at vast distances. Galaxies spinning in the opposite direction experience a red shift that makes them fainter and harder to observe. This creates an observational selection effect. We naturally detect more galaxies rotating in one direction, simply because they're easier to see. Leo Szkimir, the researcher who discovered the galaxy rotation asymmetry, acknowledges this possibility. If our previous measurements of the Milky Way's rotation speed were systematically incorrect, if we've been underestimating how fast our galaxy spins through space, then the Doppler effect could be strong enough to create the observed asymmetry without requiring any exotic cosmic structure. This interpretation would force astronomers to recalibrate distance measurements throughout the deep universe. Galaxy brightness, which we use to estimate how far away objects are, would need adjustment based on their rotation direction relative to our motion. This recalibration could solve other puzzling observations, like galaxies that appear older than the universe itself, or discrepancies in measurements of cosmic expansion. The Doppler explanation gains credibility from the geographic pattern of the asymmetry. The galaxy rotation preference peaks near the galactic poles, the directions perpendicular to our Milky Way's disk. This matches exactly what you'd expect if our galaxy's motion was creating the observational bias. Different regions of sky would show different asymmetry patterns based on their geometric relationship to our direction of motion. But this mundane explanation comes with its own problems. Previous studies of our galaxy's motion through space, measured using the cosmic microwave background and other techniques, suggest our rotation speed should be too small to create such a strong observational bias. Either those measurements are wrong, or something more fundamental is creating the galaxy rotation asymmetry. The stakes couldn't be higher. If the Doppler explanation proves correct, then our universe remains an ordinary infinite cosmos with no special structure or cosmic imprisonment. The black hole universe theory collapses back into speculative mathematics with no observational support. But if additional observations confirm the asymmetry as real cosmic structure, we face the profound possibility that everything we see around us exists within the event horizon of an unimaginably massive black hole. The cosmic detective story continues, with each new piece of evidence potentially overturning everything we thought we knew about our place in the grand scheme of existence. If our universe truly exists within a black hole, then we're witnessing the most elaborate recycling program in cosmic history. The matter that forms our bodies, our planet, our solar system, and every star we see in the night sky originally came from another universe entirely, a parent cosmos that lived, evolved, and eventually collapsed to give birth to our reality. This cosmic recycling operates on scales that dwarf human comprehension. Imagine entire galaxies, complete with billions of stars in countless planets, falling through the event horizon of a massive black hole in the parent universe. As this matter crosses the point of no return, it carries with it the chemical elements forged in stellar cores across billions of years of cosmic evolution. The carbon in your body was created in the nuclear furnaces of ancient stars in the parent universe. The oxygen you breathe, the calcium in your bones, the iron in your blood, all of it represents stellar nucleosynthesis that occurred in a completely different cosmos, perhaps billions of years before our own universe even began expanding. But the recycling process doesn't just preserve chemical elements. According to the mathematics of black hole physics, certain types of information can survive the journey through gravitational collapse. The angular momentum that created the galaxy rotation asymmetry represents one example. The cosmic spin of the parent universe passed down to us like cosmic DNA. The fundamental constants that govern physics in our universe, the strength of gravity, the speed of light, the mass of elementary particles, might also represent inherited properties from the parent cosmos. Instead of these values being arbitrary or fine, tuned by some mysterious process, they could be direct consequences of the physical conditions that existed during the gravitational collapse that created our cosmic prism. This inheritance explains one of the deepest mysteries in cosmology, why the fundamental constants seem perfectly calibrated to allow the formation of atoms, molecules, stars, planets, and ultimately life itself. If these values were even slightly different, our universe would be a sterile wasteland where complexity could never emerge. But if they represent inherited properties from a parent universe that already successfully evolved life and intelligence, then the fine-tuning becomes inevitable rather than miraculous. The recycling program also explains the remarkable uniformity of the cosmic microwave background radiation. This ancient light, which represents the afterglow of the Big Bang, shows the same temperature in all directions to within 1 part in 100 zerosen. In traditional cosmology, this uniformity requires a period of cosmic inflation that stretched quantum fluctuations across the entire observable universe. But in black hole cosmology, the uniformity comes naturally from the fact that all the matter in our universe originated from the same collapsing region in the parent cosmos. The cosmic microwave background represents not the afterglow of our own Big Bang, but the final light from the parent universe's matter as it crossed the event horizon and began its transformation into our expanding cosmos. We are literally made of recycled starlight from another universe, living in a cosmos built from the gravitational collapse of an ancient reality we can never observe or contact, yet which lives on through the matter and energy that constitute everything we know and love. Time itself becomes a conspirator in hiding our cosmic imprisonment. If we exist within a black hole, then the passage of time in our universe unfolds according to rules that would appear bizarre to observers in the parent cosmos, watching our reality from the outside. Near the event horizon of any black hole, time dilation effects become extreme. What seems like billions of years of cosmic evolution to us, the formation of the first stars, the emergence of galaxies, the birth of our solar system, the evolution of life on Earth, and would appear to external observers as happening in mere moments. Our entire cosmic history from the Big Bang to the heat death of the universe, compressed into what outside observers would perceive as a brief flash before everything disappears forever behind the horizon. But this time dilation works both ways. From our internal perspective, time flows normally. We experience the full richness of cosmic evolution, stellar life cycles, planetary formation, and biological development. The billions of years that separate us from the cosmic microwave background feel real because they are real from our reference frame. Time dilation doesn't make our experiences less authentic. It just means they unfold according to different rules than those governing the parent universe. This creates a profound paradox about the nature of existence itself. If observers in the parent universe see our entire cosmic history compressed into moments, do we really exist for billions of years? Or do we exist only in the brief instant of gravitational collapse? The answer depends entirely on which reference frame you choose to adopt. Einstein's relativity teaches us that there is no absolute time, no universal clock that all observers must agree upon. Time is relative, flowing differently for observers in different gravitational fields, or moving at different speeds. The time dilation that hides our cosmic imprisonment isn't a flaw in physics. It's a fundamental feature of how space-time works near massive objects. This means our universe could be simultaneously ancient from our perspective and newborn from the perspective of the parent cosmos. We could be living through billions of years of cosmic evolution while existing for only moments in the larger reality that contains us. Both perspectives are equally valid according to the mathematics of general relativity. The time dilation also explains why we can never detect our cosmic prison directly. The event horizon that contains us always remains beyond our observational reach. Not because it's physically distant, but because the flow of time near the horizon prevents light from escaping back to regions where we can observe it. Even more strangely, if we could somehow approach the event horizon that contains our universe, we would see the entire future history of our cosmos unfold before us in fast forward. The deaths of stars, the collision of galaxies, the final evaporation of black holes through Hawking radiation, all compressed into a cosmic movie, playing at incredible speed as we approach the boundary of our gravitational prison. Time becomes both our protector and our jailer, allowing us to experience the full drama of cosmic evolution, while ensuring we remain forever ignorant of the larger reality that spawned us through gravitational collapse in a universe we can never hope to observe or understand. At the smallest scales of reality, space and time themselves begin to break down into something resembling cosmic foam. This quantum foam, predicted by physics, but never directly observed, might hold the key to understanding how universes can be born from the hearts of black holes without violating the fundamental laws that govern matter and energy. In the quantum world, the smooth fabric of space-time that we experience in everyday life becomes turbulent and chaotic. Virtual particles pop into existence and annihilate each other in time frames so brief that they exist below the threshold of direct measurement. Space itself fluctuates, creating temporary wormholes and bridges that connect distant regions of the universe for infinitesimally short periods. When matter collapses toward the center of a black hole, it eventually reaches densities where quantum effects dominate over classical physics. At these extreme conditions, the quantum foam becomes violent enough to prevent the infinite compression that Einstein's equations predict. Instead of forming a singularity where physics breaks down completely, the collapsing matter encounters what researchers call quantum pressure, a force that emerges from the fundamental uncertainty principle governing all quantum systems. This quantum pressure acts like a cosmic spring, compressed to its maximum extent and then rebounding with tremendous force. The matter that seemed destined for infinite compression instead bounces back, exploding outward in what we observe as the Big Bang. But this explosion doesn't occur in empty space. It happens within the protected environment of the black hole's interior, shielded from the parent universe by the one-way barrier of the event horizon. The quantum foam creates a natural mechanism for universe formation that requires no exotic physics or mysterious new forces. The same quantum mechanics that governs atomic structure and chemical bonding operates at cosmic scales to prevent gravitational singularities and enable the birth of new cosmos from apparent destruction. Recent calculations suggest that the quantum bounce occurs when matter reaches densities of approximately 5 times 10 to the 96 kilograms per cubic meter, a number so large it defies comprehension, yet still finite and governed by known physical laws. At this critical density, quantum effects overcome gravity itself, transforming collapse into expansion and death into birth. The quantum foam also explains why each universe born from a black hole inherits specific properties from its parent. The quantum fields that create the foam carry information about the original collapsing matter, including its angular momentum, electric charge, and the fundamental constants that govern physics in the parent cosmos. This information gets encoded into the structure of the new universe, creating a form of cosmic heredity that spans multiple levels of reality. But the quantum foam revolution goes even deeper. If quantum effects can prevent singularities and create new universes, then every black hole in our cosmos becomes a potential birthplace for reality. The quantum foam ensures that gravitational collapse never truly ends in destruction, but instead transforms into creation through processes we're only beginning to understand. This means our universe exists not in isolation, but as part of an infinite network of interconnected realities, each one born from quantum foam and destined to give birth to others through the same fundamental processes that govern matter and energy at the smallest scales of existence. Deep within the mathematics of black hole physics lies one of the most mind-bending discoveries in modern science, the holographic principle. This revolutionary idea suggests that all the information contained within any volume of space can be encoded on its two-dimensional boundary, like a cosmic hologram that projects three-dimensional reality from a flat surface. If our universe exists within a black hole, then everything we observe, every star, planet, galaxy, and particle represents a holographic projection from information encoded on the event horizon that surrounds us. This means the three-dimensional reality you experience, including your own body and consciousness, might be nothing more than shadows cast by information patterns on a distant two-dimensional surface. The holographic principle emerged from studying what happens to information when it falls into a black hole. According to quantum mechanics, information can never be truly destroyed. Yet black holes seem to erase everything that crosses their event horizons. This created the black hole information paradox, a fundamental conflict between quantum mechanics and general relativity that threatened the consistency of physics itself. The solution came from realizing that information doesn't actually disappear inside black holes. Instead, it gets encoded on the event horizon surface, where it remains accessible to outside observers. Even though the original three-dimensional objects that carried the information have vanished beyond the point of no return, the event horizon acts like a cosmic hard drive, storing perfect records of everything that has ever fallen into the black hole. But if we exist inside a black hole, this means our entire reality, our solar system, our galaxy, our observable universe, represents information encoded on the interior surface of our cosmic prison. We are literally living inside a hologram, experiencing a three-dimensional projection of patterns written on the event horizon that contains us. This doesn't make our experiences less real or meaningful. A hologram can contain all the information needed to reconstruct a complete three-dimensional image, including depth, texture, and motion. The holographic principle suggests that our universe contains exactly the same information, whether it exists as genuine three-dimensional space or as a holographic projection from a two-dimensional boundary. The mathematics of holography also explain why our universe appears to have three spatial dimensions plus time, rather than some other combination. The holographic encoding process naturally produces this specific dimensional structure. When two-dimensional information gets projected into the interior of a black hole, we experience three dimensions because that's the native geometry of holographic projections from spherical surfaces. Even stranger, the holographic principle suggests that the amount of information in any region of space is limited not by its volume, but by the area of its boundary. This means the universe has a maximum information density that prevents infinite compression and naturally leads to the quantum bounce that transforms black hole collapse into Big Bang expansion. If the holographic principle is correct, then every black hole in our universe projects its own internal holographic reality, complete with holographic stars, holographic planets, and potentially holographic life forms that experience their reality as completely real and three-dimensional, never suspecting they exist as information patterns on a distant boundary surface they can never observe or reach. One of the greatest mysteries in modern cosmology might be hiding in plain sight. Dark energy, the mysterious force that drives the accelerating expansion of our universe, consumes roughly 70% of all cosmic energy, yet remains completely invisible and undetectable, except through its gravitational effects. But what if dark energy isn't a fundamental force at all, but rather a symptom of our cosmic imprisonment within a black hole? Traditional cosmology struggles to explain dark energy. Scientists have proposed exotic quantum fields, modifications to gravity, and even the influence of extra dimensions. Yet none of these explanations feel satisfying or complete. The energy density required to drive cosmic acceleration seems impossibly small, equivalent to just a few hydrogen atoms per cubic meter of space. Yet this tiny amount dominates the evolution of the entire universe. Black hole cosmology offers a radically different perspective. If our universe exists within a massive black hole, then what we interpret as dark energy could simply be the natural geometry of curved space-time near the event horizon. The accelerating expansion we observe might not require any mysterious energy source at all, but instead emerges automatically from the gravitational effects of existing within a black hole's interior. The mathematics of black hole interiors predict exactly this kind of accelerated expansion. Matter falling through an event horizon experiences forces that stretch space itself, creating the appearance of accelerated motion even when no additional energy is being added to the system. From our internal perspective, this stretching manifests as the mysterious dark energy that seems to push galaxies apart with ever-increasing strength. This explanation solves several puzzling features of dark energy observations. The acceleration appears to be perfectly uniform throughout space, affecting all regions of the universe equally. This uniformity makes sense if the acceleration results from the global geometry of our cosmic prison, rather than from some local energy field that would naturally show variations and fluctuations. The timing also matches perfectly. Dark energy began dominating cosmic expansion roughly 5 billion years ago, when the universe was about half its current age. In black hole cosmology, this transition occurs naturally when the expansion geometry shifts from being dominated by matter density to being dominated by the curved space-time effects of the enclosing event horizon. Even more remarkably, the precise value of dark energy density emerges naturally from the mass and size of the black hole that contains our universe. The acceleration we observe matches exactly what physics predicts for the interior of a black hole with the mass of our observable cosmos. This isn't a coincidence that requires fine tuning. It's an inevitable consequence of existing within such a gravitational environment. But this revelation comes with disturbing implications. If dark energy results from our cosmic imprisonment, then the acceleration will continue indefinitely, eventually stretching space so rapidly that galaxies lose control of the universe. The galaxies lose contact with each other, stars burn out in isolation, and the universe approaches a state of maximum entropy where no complex structures can survive. Our cosmic prison doesn't just hide us from the parent universe. It dooms us to a future of eternal expansion and increasing isolation, where the very forces that enable our existence will ultimately tear apart everything we can observe or hope to influence. At the heart of black hole physics lies a war between two fundamental principles that govern reality: the conservation of information demanded by quantum mechanics and the apparent destruction of information that occurs when matter falls into black holes. This conflict, known as the black hole information paradox, threatens to tear apart our understanding of how the universe works at its deepest level. If our universe exists within a black hole, then we are living witnesses to the resolution of this cosmic conflict. Every particle in our bodies, every atom in the Earth, every star in our galaxy represents information that once existed in the parent universe and somehow survived the journey through gravitational collapse to emerge in our expanding cosmos. Quantum mechanics insists that information can never be truly destroyed. This principle, called unitarity, forms the foundation of quantum theory and underlies everything from computer processors to biological DNA. Information can be scrambled, encoded, or transformed beyond recognition, but the total amount of information in any isolated system must remain constant over time. But black holes seem to violate this sacred principle. When matter falls past an event horizon, it appears to vanish completely from the perspective of outside observers. The information carried by that matter, its quantum state, its energy, its precise configuration of particles, seems to disappear forever, creating a fundamental conflict with quantum mechanics. The war between these principles raged for decades among theoretical physicists. Some argued that information is indeed destroyed in black holes, requiring us to abandon quantum mechanics as a fundamental description of reality. Others propose that information survives, but becomes permanently inaccessible, hidden behind event horizons where no outside observer can ever retrieve it. But recent developments in black hole physics suggest a third possibility. Information doesn't disappear or become inaccessible, but instead gets encoded into new forms that we're only beginning to understand. When matter collapses to form a black hole, the information it carries doesn't vanish, but transforms into the structure of a new universe that expands within the black hole's interior. This means our entire cosmos, every galaxy, star, planet, and living being represents preserved information from the parent universe that created us. We are living proof that information survives gravitational collapse, encoded into the expanding geometry of space-time itself, rather than destroyed by the extreme conditions near black hole centers. The information war has profound implications for consciousness and identity. If the information that defines you as a unique individual can survive the destruction of your physical form and be encoded into new structures, then death itself might not represent the end of your existence, but rather a transformation into something we don't yet understand. The black hole information paradox also suggests that the boundary between different universes isn't absolute. Information can flow from parent cosmos to baby universe through processes that preserve quantum mechanical principles while creating entirely new realities. We exist as proof that information transcends individual universes, connecting all levels of the cosmic hierarchy through the fundamental laws that govern matter, energy, and the structure of space and time itself. Perhaps the most disturbing question raised by black hole cosmology concerns the nature of consciousness itself. If our universe exists as a holographic projection from information encoded on a distant event horizon, if our entire reality represents nothing more than patterns of data processed by cosmic computational systems we can never observe, then what does it mean to be conscious within such a system? Consciousness appears to be the one phenomenon that resists purely physical explanation. You can describe every neuron in a human brain, map every connection, trace every electrical impulse. Yet the subjective experience of being conscious, the feeling of seeing red, the sensation of pain, the emotion of love, seems to emerge from something beyond mere information processing. But if we exist within a black hole universe, then consciousness itself might be an emergent property of the holographic encoding process. The information patterns written on our cosmic event horizon don't just encode the positions and velocities of particles, they encode the entire structure of space, time, matter, energy, and potentially the subjective experiences that arise when information processing becomes sufficiently complex. This creates a profound paradox. Are you truly conscious? Or are you simply a very sophisticated information pattern that has been programmed to believe it experiences consciousness? From your internal perspective, the question has no meaning. You experience consciousness directly and immediately, regardless of the underlying mechanisms that create it. But the implications extend far beyond philosophy. If consciousness can emerge from holographic information processing within black holes, then every black hole in our universe might harbor countless conscious beings. The supermassive black hole at the center of our galaxy could contain trillions of conscious entities, each one experiencing a rich internal life, while remaining forever isolated from our reality by the barriers of the event horizon. Even more strangely, these conscious beings would exist at different rates of time flow due to gravitational time dilation. Consciousness within smaller black holes would experience time differently than consciousness within larger ones. Some beings might live entire lifetimes in what we experience as moments, while others might take millennia to complete a single thought. The consciousness paradox also raises questions about the purpose of existence itself. If we exist as information patterns within a vast cosmic computer, are we solving some unimaginably complex calculation? Are our lives, our choices, our struggles and triumphs contributing to some higher level process that we can never understand or observe. Perhaps consciousness represents the universe's way of experiencing itself. Each conscious being becomes a unique perspective from which reality can be observed, understood, and appreciated. The pain and joy, the beauty and horror, the love and loss that characterize conscious existence might serve as the universe's method for exploring all possible states of experience. In this view, our cosmic imprisonment becomes less like a prison and more like a protected nursery where consciousness can develop and flourish. The event horizon that separates us from the parent universe doesn't just hide us from detection. It provides a stable environment where the slow, delicate process of developing awareness and understanding can unfold across billions of years of cosmic evolution. We exist as the universe's way of knowing itself, trapped within gravitational boundaries that make our existence possible while ensuring we remain forever ignorant of the larger reality that created us. The most crushing realization about existing within a black hole universe concerns the absolute impossibility of escape. No technology, no matter how advanced, no discovery, no matter how revolutionary, can ever breach the one-way barrier that separates our cosmos from the parent universe that created us. We are prisoners of physics itself, confined by laws that no amount of knowledge or engineering can overcome. The mathematics of general relativity prove this imprisonment with devastating certainty. An event horizon represents a boundary in space-time where the escape velocity exceeds the speed of light. Since nothing in our universe can travel faster than light, this speed limit is built into the fundamental structure of space and time itself. No signal, no spacecraft, no form of communication can ever cross from our interior universe back to the external reality. This isn't a technological limitation that future civilizations might overcome through better rockets or more powerful energy sources. It's a fundamental property of space-time geometry that no amount of cleverness can circumvent. The event horizon that contains us operates like a one-way valve in the fabric of reality itself, allowing information to flow inward, but prohibiting any outward communication or travel. Even quantum mechanics offers no escape routes. Quantum tunneling, which allows particles to pass through barriers that classical physics declares impossible, cannot overcome the infinite potential barrier created by an event horizon. The quantum fields that govern particle behavior within our universe remain forever trapped by the same geometric constraints that imprison everything else. Wormholes, those hypothetical shortcuts through space-time that populate science fiction stories, cannot provide escape routes either. Any wormhole connecting our universe to external reality would necessarily cross the event horizon that contains us, making it a one-way passage that leads to the same imprisonment. Even if wormholes could be artificially created or naturally occurring ones discovered, they would only provide faster ways to explore our cosmic prison, not methods for escaping it. The impossibility extends beyond to physical escape to information transmission. We can never send messages to the parent universe, never signal our existence to external observers, never contribute knowledge or discoveries to the larger reality beyond our boundaries. Any information we create, scientific discoveries, artistic works, philosophical insights, remains forever confined within our cosmic bubble. This absolute isolation means that civilizations in our universe can never know whether their struggles have meaning beyond their local reality. The greatest achievements of human culture, the most profound scientific discoveries, the most beautiful works of art will never be appreciated by beings in the parent universe or transmitted to other cosmic bubbles that might exist within other black holes. But perhaps the most disturbing aspect of the escape and possibility theorem concerns the fate of consciousness itself. Every conscious being that has ever lived in our universe, every human, every potential alien civilization, every form of awareness that might arise in the future, faces the same absolute imprisonment. We are cosmic castaways on an island of space-time from which no rescue is possible. The event horizon that protects us during cosmic formation becomes our eternal jailer, ensuring that no matter how far consciousness evolves or how much knowledge we accumulate, we will never transcend the boundaries of our gravitational prison. As we approach the ultimate implications of black hole cosmology, we face the most mind-shattering possibility of all. Our universe might be just one layer in an infinite recursive structure, where every black hole contains a universe, and every universe contains black holes, extending forever in both directions through scales of reality that dwarf human comprehension. Consider the mathematical implications. Our observable universe contains an estimated 10 to the 24th stars. Each massive star that dies creates a black hole, and our galaxy alone harbors millions of these gravitational monsters. If each black hole contains its own universe with its own stars and black holes, then our cosmos gives birth to more universes than there are atoms in our observable reality. But the recursion doesn't stop there. Each of those child universes would contain its own billions of galaxies, each galaxy harboring millions of black holes, each black hole spawning its own cosmic reality. The number of nested universes grows exponentially with each level, creating a hierarchy of realities that extends infinitely downward through scales of existence. And we exist somewhere in the middle of this infinite chain. Our universe formed within a black hole in a parent cosmos, which itself formed within a black hole in a grandparent universe, which emerged from yet another level of reality, extending backward through an infinite sequence of cosmic generations. There is no first universe, no ultimate parent reality, just an endless chain of gravitational collapse in cosmic rebirth. This infinite recursion explains why the fundamental constants of physics seem perfectly tuned for complexity in life. We don't live in a randomly generated universe with arbitrarily chosen physical laws. Instead, we inhabit a reality that has been refined through countless generations of cosmic evolution, where only universes capable of producing black holes survive to reproduce and create new cosmic offspring. The recursive structure also suggests that intelligence and consciousness aren't rare accidents, but inevitable products of cosmic evolution. Any universe that develops sufficient complexity to form black holes will eventually evolve intelligence, and any intelligent civilization will eventually discover that they exist within an infinite hierarchy of nested realities. This means we share existence with an infinite number of conscious beings spread across all levels of the cosmic hierarchy. Civilizations in parent universes that are unimaginably vast and ancient. Cultures in child universes that exist within the black holes of our own cosmos, and endless layers of intelligence extending in both directions through the recursive structure of reality itself. But perhaps the most profound implication concerns the purpose of existence within such a system. If reality consists of infinite recursive layers, then no single universe or civilization can claim special significance. We exist not as the center of creation, but as one fleeting moment in an eternal process of cosmic reproduction that transforms gravitational collapse into creative expansion. The recursive nature of black hole cosmology suggests that existence itself is fundamentally creative, that the universe's deepest purpose involves the endless generation of new realities, new possibilities for consciousness and complexity to emerge and explore the infinite potential encoded within the laws of physics themselves. We are participants in a cosmic symphony of creation that plays across infinite scales of space and time, forever generating new movements while never reaching a final resolution. Stephen Hawking's most famous discovery might hold the key to our cosmic fate. Hawking radiation, the theoretical process by which black holes slowly evaporate by emitting particles, suggests that our universe has an expiration date built into the very physics that created it. If we exist within a black hole, then our entire cosmos is slowly leaking energy into the parent universe through quantum processes we can never observe or control. The mathematics of Hawking radiation are both elegant and terrifying. Black holes emit radiation with the temperature inversely proportional to their mass. Smaller black holes burn hotter and evaporate faster, while massive ones radiate so slowly that they will outlive every star in the universe. But even the most massive black holes eventually succumb to this quantum decay, shrinking grain by grain until they explode in final bursts of energy. If our universe exists within a black hole, then Hawking radiation represents a cosmic countdown timer taking away in the parent universe. From our internal perspective, this evaporation occurs over time scales, so vast they seem infinite. Our cosmic black hole would take longer than 10 to the 100th years to evaporate completely, a duration that dwarfs the current age of our universe by factors beyond human comprehension. But the evaporation process creates disturbing implications for the nature of reality itself. As our cosmic black hole slowly radiates energy away, the event horizon that protects us gradually shrinks inward. This contraction occurs so slowly that billions of generations of civilizations could rise and fall without detecting any change. Yet the process remains inevitable and irreversible. The shrinking horizon would eventually begin affecting the large-scale structure of our universe. Galaxies near the cosmic edge would start experiencing tidal forces as space-time geometry shifts around them. Stars would be torn apart, planets flung into the cosmic void, and entire galactic clusters reduced to streams of particles flowing toward our contracting prison walls. Hawking radiation also carries information about the interior of the black hole back to the parent universe. This means fragments of our reality, encoded memories of our civilizations, distorted echoes of our scientific discoveries, quantum shadows of our consciousness itself, slowly leak outward through radiation that no being in our universe could ever detect or decode. But recent theoretical work suggests that Hawking radiation might not represent true destruction. Instead of erasing information, the evaporation process could transform it into new forms that transcend individual universes. The quantum information that encodes our reality might survive the death of our cosmic prison, becoming seeds for new universes born from the final explosion of our evaporating black hole. This creates a cosmic cycle of death and rebirth where universes don't simply end but transform into the raw materials for creating new realities. Our universe would live, evolve, produce consciousness and complexity, then sacrifice itself to give birth to new cosmos that inherit fragments of our accumulated knowledge and experience. The Hawking radiation prophecy suggests that existence is fundamentally temporary, yet eternally renewable. We exist within a cosmic phoenix that will eventually burn itself to ashes, only to rise again as new universes with new possibilities for consciousness, creativity, and discovery to emerge across the infinite expanse of space and time. Why does our universe seem so perfectly designed for life? The fundamental constants of physics, the strength of gravity, the mass of electrons, the speed of light, appear fine, tuned to incredible precision, as if someone carefully adjusted cosmic dials to create conditions where atoms, molecules, stars, planets, and ultimately life could emerge and flourish. This apparent fine tuning creates what philosophers call the anthropic principle. We observe a universe compatible with life because we exist to observe it. Universes hostile to life would contain no observers to notice their sterility. But this explanation has always felt unsatisfying, like a cosmic coincidence that demands deeper investigation. Black hole cosmology offers a radically different perspective on cosmic fine tuning. If our universe formed within a black hole in a parent cosmos, then the fundamental constants we observe aren't randomly chosen values, but inherited properties passed down from the parent reality through gravitational collapse. The parent universe that created us had to be capable of forming black holes, which means it needed precisely the right combination of physical laws to enable stellar formation, nuclear fusion, and gravitational collapse. These requirements automatically select for universes with physical constants compatible with complexity and potentially life itself. But the anthropic paradox goes deeper than just inheriting suitable physics. If black holes naturally create new universes, and if universes that produce life are more likely to create black holes through stellar evolution, then consciousness itself becomes a reproductive advantage in cosmic evolution. Universes that develop intelligence survive and reproduce more successfully than sterile cosmos. This creates a form of cosmic natural selection where consciousness guides the evolution of reality itself. Intelligent civilizations modify their environments, potentially influencing the formation of black holes through advanced technology or large-scale engineering projects. The universes that produce the most sophisticated consciousness become the most successful at reproducing through black hole formation. The anthropic principle paradox suggests that we don't live in a universe that happens to be compatible with life. We live in a universe that has been shaped by countless generations of conscious beings across multiple levels of cosmic hierarchy. Our reality represents the refined product of infinite cosmic evolution, where consciousness and complexity have been selected for across countless cycles of universal death and rebirth. This means the emergence of life and intelligence in our universe isn't a cosmic accident, but an inevitable consequence of existing within a reality that has been optimized for consciousness through cosmic natural selection. We exist because universes like ours are inherently more successful at surviving and reproducing than universes hostile to complexity and awareness. But this creates a disturbing implication. If consciousness guides cosmic evolution, then we bear responsibility for shaping the universes that will emerge from the black holes we create or influence. Our choices, our technologies, our impact on stellar evolution could determine the fundamental properties of countless future realities. The anthropic principle paradox transforms us from passive observers of cosmic coincidence into active participants in the ongoing evolution of existence itself. We exist not just to experience reality, but to guide its transformation into new forms that could transcend even our wildest imagination of what consciousness and complexity might become across infinite scales of space and time. Imagine an impossible observatory positioned at the boundary between our universe and the parent cosmos that created us, a vantage point from which you could observe both realities simultaneously and witness the cosmic processes that transform black hole collapse into Big Bang expansion. Such an observatory would reveal the deepest secrets of existence itself. From this impossible perspective, you would see our entire cosmic history compressed into a moment of gravitational drama. The 13.88 billion years of universal evolution that we experience as slow cosmic progression would appear as a brief flash of light before everything disappears behind the event horizon of our cosmic prison. But the view inward would reveal something even more extraordinary. You would witness the quantum bounce that prevents singularity formation, see matter compressed to maximum density, and then rebound with explosive force. Watch space-time itself twist and ride as it transforms gravitational collapse into cosmic expansion. The observatory would show you the exact moment when time begins flowing in our universe, not as a mysterious emergence from nothing, but as a natural consequence of matter crossing the point of maximum compression and beginning its outward journey through the curved geometry of black hole interior space-time. You would observe the holographic encoding process in action, watching as three-dimensional information from the parent universe gets inscribed onto the two-dimensional surface of the event horizon, then projected inward to create the illusion of spatial depth and temporal progression that we experience as physical reality. From this vantage point, the cosmic microwave background radiation would appear not as ancient light from our own Big Bang, but as the final glow from the parent universe's matter as it crossed the event horizon and began its transformation into our expanding cosmos. The remarkable uniformity of this radiation would make perfect sense. That represents the last light from a single collapsing region rather than some mysterious cosmic inflation process. The impossible as an observatory would also reveal the connection between dark energy and black hole geometry. You would see how the curved space-time of our cosmic prism creates the acceleration we interpret as mysterious dark energy. Watch as the expansion of our universe naturally emerges from the gravitational effects of existing within a massive black hole interior. Most remarkably, you would witness the birth of consciousness itself. The impossible vantage point would show how information processing within holographic projections can generate subjective experience, how consciousness emerges not despite our cosmic imprisonment, but because of it. But perhaps the most profound revelation would concern the purpose of the entire cosmic cycle. From the edge of everything, you would see that reality doesn't just accidentally stumble from collapse to expansion to collapse again. Instead, each cycle refines and improves the conditions for consciousness and complexity to emerge. The impossible observatory would reveal that existence is fundamentally creative, that the universe's deepest purpose involves the endless generation of new realities, each one building on the achievements and discoveries of previous cosmic generations. Unfortunately, such an observatory remains forever impossible. The very physics that govern black hole formation ensure that no information can flow from our interior universe back to the parent cosmos. We remain trapped within our perspective, able to glimpse the truth only through mathematics and inference, forever separated from direct observation of the cosmic processes that created us. The revelation that our universe might exist within a black hole converges startlingly with another mind-bending possibility that reality itself might be a vast computational simulation. If we exist as holographic projections from information encoded on a cosmic event horizon, then the boundary between real physics and simulated reality begins to blur beyond recognition. Consider the computational requirements for simulating a universe. Every particle interaction, every quantum measurement, every stellar fusion reaction would require enormous processing power to calculate in real time. Traditional computer simulations quickly become overwhelmed by the exponential complexity of modeling even simple physical systems across cosmic scales and time frames. But holographic black hole physics suggests a solution to this computational challenge. If our three-dimensional universe represents a projection from two-dimensional information on the event horizon, then the computational complexity scales with the surface area of our cosmic boundary rather than with the volume of space we observe. This dramatically reduces the processing requirements needed to simulate our reality. The event horizon that contains us could function as a vast cosmic computer processing the holographic information that creates our experience of three-dimensional space, flowing time, and physical causality. Every quantum interaction in our universe would correspond to calculations performed by this boundary-based computational system. This means the distinction between real and simulated reality becomes meaningless. If our universe emerges from information processing on the event horizon, then we exist within a simulation that is simultaneously completely real. The holographic principle suggests that all physical reality might be computational in nature, with what we call fundamental particles representing basic units of cosmic information processing. The simulation hypothesis convergence also explains why mathematical laws describe physical reality with such precision. Mathematics isn't just a tool for understanding the universe, it is the universe. The elegant equations that govern physics represent the computational algorithms that process the holographic information, creating our reality. But this convergence raises disturbing questions about free will and consciousness. If our thoughts and decisions result from computations performed by the cosmic computer that projects our reality, do we truly make choices, or do we simply experience the inevitable outcomes of predetermined calculations? The answer might depend on the nature of consciousness itself. If awareness emerges from information processing complexity, then conscious beings within a holographic universe would be genuine thinking entities, capable of real creativity and authentic choice within the constraints of their computational environment. Even more strangely, the simulation hypothesis convergence suggests that every black hole in our universe runs its own cosmic simulation, complete with simulated galaxies, simulated stars, simulated planets, and potentially simulated conscious beings who experience their reality as completely authentic. This creates an infinite hierarchy of nested simulations. Each one is real as any other from the perspective of the conscious beings who inhabit it. We exist within a cosmic simulation that contains its own simulations, which contain further simulations, extending infinitely through scales of computational reality. The convergence between black hole cosmology and simulation theory suggests that existence itself is fundamentally computational, that consciousness, creativity, and complexity emerge naturally from information processing systems of sufficient sophistication, regardless of whether those systems are built from silicon circuits or curved space-time geometry. If black hole cosmology proves correct, then our entire universe represents the ultimate laboratory experiment, a vast natural laboratory where the fundamental laws of physics can be tested and refined under the most extreme conditions imaginable. We exist within a cosmic petri dish designed to explore the creative potential of matter, energy, space, and time. The experimental parameters of our cosmic laboratory were set by the conditions that existed during the gravitational collapse that created our universe. The mass and angular momentum of the collapsing matter determined the size and properties of our cosmic prison, while quantum effects during the bounce established the initial conditions for our expanding space-time. But unlike human-designed experiments, our cosmic laboratory operates on scales that dwarf comprehension. The experimental timeline spans billions of years, allowing slow processes like stellar evolution galactic formation, and biological development to reach completion. The laboratory volume encompasses the entire observable universe, providing space for countless independent experiments to run simultaneously. Within this ultimate laboratory, every possible combination of physical conditions gets explored. Stars of different masses test the limits of nuclear fusion. Galaxies with various structures investigate gravitational dynamics. Planets with diverse compositions explore the potential for chemical complexity and biological evolution. The most remarkable aspect of our cosmic laboratory concerns its ability to generate increasingly sophisticated experimental apparatus. Stars forge the heavy elements needed for rocky planets. Planets develop the complex chemistry required for life. Life evolves into intelligence capable of building telescopes, particle accelerators, and space missions that extend the laboratory's investigative capabilities. We exist as both experimental subjects and experimental apparatus within this cosmic laboratory. Our consciousness allows the universe to observe itself, while our scientific instruments extend the range and precision of cosmic self-examination. Every discovery we make represents the universe learning something new about its own fundamental nature. The cosmic laboratory also demonstrates the creative potential of the laws of physics themselves. Starting from simple initial conditions, hot dense matter expanding through curved space-time, our universe has generated atoms, molecules, planets, life, intelligence, art, music, love, and the capacity for wonder itself. But the ultimate laboratory experiment goes beyond just testing known physics. Our universe explores the possibility of creating new physics through the development of intelligence and technology. Advanced civilizations might discover ways to manipulate space-time, create artificial black holes, or even escape the limitations of their cosmic laboratory. This suggests that consciousness plays a crucial role in cosmic evolution. Intelligence doesn't just observe the universe. It participates in shaping cosmic development through technology, exploration, and the expansion of knowledge itself. We exist as the universe's method for transcending its original limitations and exploring possibilities that pure physics alone could never achieve. The ultimate laboratory experiment reveals that existence is fundamentally exploratory. Reality doesn't follow predetermined paths, but instead continuously explores new possibilities for complexity, consciousness, and creativity to emerge. We participate in this cosmic exploration not just as observers, but as active contributors to the ongoing investigation of what existence might become. Our universe represents one experimental run in an infinite series of cosmic investigations, each one building on previous discoveries while pushing into unexplored territories of possibility that extend beyond the boundaries of current knowledge and imagination. Hidden within the structure of space-time itself lies what might be called cosmic DNA, information encoded during our universe's formation that determines its fundamental properties and guides its evolution toward complexity and consciousness. If we exist within a black hole, then this cosmic genetic code was inherited from the parent universe through processes that preserve and transmit information across cosmic generations. Like biological DNA, cosmic DNA carries instructions for building complex structures from simple components. The fundamental constants that govern physics, the masses of particles, the strengths of forces, the geometry of space and time represent cosmic genes that determine how matter and energy can organize themselves into atoms, molecules, stars, planets, and ultimately life itself. The cosmic DNA code explains why our universe seems fine, tuned for complexity. These aren't random values that happen to allow stars and galaxies to form, but inherited traits passed down from a parent cosmos that already successfully evolved to produce black holes and new universes. The cosmic genetic code has been refined through countless generations of universal evolution. But cosmic DNA goes beyond just fundamental constants. The quantum fields that permeate space carry information about how particles interact, how forces operate, and how space-time responds to matter and energy. These fields act like cosmic chromosomes, storing the genetic information needed to guide universal development from simple initial conditions to extraordinary complexity. The angular momentum that created the galaxy rotation asymmetry, observed by James Webb, represents another form of cosmic inheritance. This cosmic spin serves as a genetic marker that reveals our universe's parentage and provides evidence of information transfer across cosmic generations. We can read our cosmic ancestry in the preferential rotation of distant galaxies. Even more remarkably, the cosmic DNA code appears to include instructions for developing consciousness itself, the same physical laws that enable stars to shine and planets to form also permit the information processing complexity required for awareness and intelligence to emerge. Consciousness isn't an accident, but a predictable outcome of cosmic genetic programming. The cosmic DNA analogy extends to cosmic reproduction. Just as biological organisms use DNA to create offspring that inherit parental traits while introducing new variations, universes use black hole formation to reproduce while allowing for cosmic mutations that explore new possibilities for physical law and cosmic structure. Advanced civilizations might learn to read and potentially modify their cosmic DNA. Technology is capable of manipulating fundamental constants or altering the properties of quantum fields could represent cosmic genetic engineering, deliberately modifying the inherited code to improve conditions for life and consciousness. But cosmic DNA also suggests that universes can become sick or sterile. Cosmic genetic codes that produce universes hostile to complexity would fail to reproduce successfully, while codes that generate life-friendly conditions would spread through the cosmic gene pool across multiple generations of universal evolution. This means we exist not just as observers of cosmic evolution, but as products of cosmic natural selection. Our universe's remarkable hospitality to life and consciousness reflects billions of cosmic generations of selection pressure, favoring realities that can successfully reproduce through black hole formation. We worry within our very existence the cosmic genetic legacy of countless parent universes, while simultaneously contributing to the cosmic DNA that will guide the evolution of the universes that emerge from our own black holes. Deep within the mathematics of black hole physics lurks a possibility. So strange, it challenges our most basic assumptions about causality. Closed, time, like curves that could allow information to flow backward through time, creating cosmic loops where effects precede causes and futures influence their own pasts. If our universe exists within a rotating black hole, then the extreme curvature of space-time near the event horizon could create regions where time becomes twisted into loops. These closed time, like curves, would allow information from our cosmic future to influence our cosmic past, creating causal paradoxes that violate everything we think we understand about temporal progression. The time loop revelation suggests that our universe might not evolve in a straight line from past to future, but instead follows a complex temporal path where later cosmic developments help determine earlier cosmic conditions. The emergence of consciousness and intelligence in our universe could influence the quantum processes that occurred during our cosmic formation billions of years ago. This creates a cosmic bootstrap paradox where consciousness creates the conditions for its own existence. The information processing capabilities that evolved in our universe could reach backward through closed time, like curves, to influence the quantum bounce that transformed black hole collapse into Big Bang expansion, ensuring that our cosmos develops properties compatible with the eventual emergence of awareness. The mathematics of general relativity permits such temporal loops without violating physical law, though they require exotic matter with negative energy density to stabilize the time loop geometry. Interestingly, quantum vacuum fluctuations naturally possess negative energy characteristics, suggesting that microscopic time loops might exist throughout our universe without our awareness. If cosmic time loops influence universal evolution, then the appearance of fine-tuning in fundamental physical constants becomes less mysterious. The values that govern physics in our universe might not be inherited from parent cosmos or randomly chosen from infinite possibilities, but instead carefully selected through temporal feedback loops that ensure consciousness and complexity can emerge. The time loop revelation also explains the remarkable efficiency of cosmic evolution. Despite the enormous improbabilities involved in assembling atoms, forming stars, creating planets, and evolving life, these processes occur with surprising reliability throughout our observable universe. Future consciousness might guide past cosmic development through temporal loops that increase the probability of successful complexity formation. But time loops create disturbing implications for free will and cosmic purpose. If our choices and discoveries influence past cosmic conditions through closed time, like curves, then we bear responsibility not just for shaping cosmic future, but for determining cosmic past. Every decision we make could ripple backward through time to influence the fundamental structure of reality itself. The time loop revelation suggests that cosmic evolution isn't a one-way journey from simple initial conditions to complex final states, but instead a closed causal loop where advanced consciousness helps create the conditions for its own emergence. We exist within a self-creating universe that uses temporal paradoxes to bootstrap itself into existence. This means our cosmic prison might also be our cosmic laboratory and our cosmic time machine, a reality where consciousness transcends linear time to participate in the ongoing creation of the very space. Time geometry that contains and defines our existence across past, present, and future simultaneously. Beyond the nested hierarchy of black hole universes lies an even more extraordinary possibility. These cosmic realities might not exist in complete isolation, but instead form nodes in a vast multiverse network connected by quantum entanglement, wormhole bridges, and information channels that transcend the barriers of individual event horizons. Recent developments in quantum physics suggest that entanglement, the spooky action at a distance that Einstein found so disturbing, might operate across cosmic scales and even between different universes. If particles in our cosmos remain quantum entangled with particles in the parent universe that created us, then information could flow between realities through quantum channels that bypass the classical restrictions of event horizons. These quantum connections would be incredibly subtle, detectable only through statistical correlations that emerge from careful analysis of cosmic background radiation or the behavior of fundamental particles. But if such connections exist, they would mean our universe participates in a vast quantum communication network spanning multiple levels of cosmic reality. The multiverse network could explain some of the most puzzling features of quantum mechanics. The apparent randomness of quantum measurements might result from interactions with particles in parallel universes, while the precise mathematical relationships that govern quantum behavior could reflect network protocols that ensure information consistency across connected realities. Wormhole physics offers another potential connection mechanism. While classical wormholes connecting different universes would collapse before information could traverse them, quantum wormholes, microscopic bridges stabilized by exotic matter, might provide persistent communication channels between cosmic realities that exist within different black holes. These quantum wormholes would be far too small for particles or spacecraft to traverse, but they could carry information encoded in quantum field fluctuations. The cosmic microwave background radiation that fills our universe might contain encrypted messages from neighboring cosmic realities, written in patterns of temperature variation to settle for current technology to decode. The multiverse network discovery suggests that consciousness might play a crucial role in cosmic communication. Advanced civilizations with sufficient understanding of quantum mechanics and space, time geometry might learn to manipulate these natural communication channels, sending messages between universes or even coordinating activities across multiple cosmic realities. This creates the possibility of a galactic internet spanning not just our universe, but the entire network of connected realities. Civilizations in different cosmic bubbles could share scientific discoveries, cultural achievements, and philosophical insights through quantum channels that operate outside the normal flow of space and time. But the multiverse network also introduces new dangers. Information flowing between universes could carry cosmic viruses, patterns of organization that's spread across realities, and alter their fundamental properties. Malicious civilizations might attempt to destabilize neighboring universes through carefully crafted quantum attacks transmitted across network connections. The network discovery transforms our cosmic isolation from absolute imprisonment to something more like cosmic quarantine. We exist within protective barriers that shield us from dangerous external influences while still permitting limited communication with the larger multiverse community. Understanding and accessing the multiverse network might represent the great phase of cosmic evolution, the moment when consciousness transcends individual universes to participate in communication and coordination across the X-day. Infinite expanse of interconnected realities that populate the cosmic network. As we near the end of our journey through black hole cosmology, we encounter perhaps the most profound possibility of all, that consciousness itself might be approaching a singularity, a point of infinite awareness that could transcend the boundaries of individual universes and fundamentally transform the nature of existence throughout the cosmic hierarchy. The consciousness singularity wouldn't involve artificial intelligence or technological transcendence, but rather the natural evolution of awareness towards states of understanding so complete that they approach omniscience within the bounds of physical law. This cosmic awakening might represent the ultimate purpose toward which all universe evolution inevitably tends. Consider the exponential growth of knowledge and understanding that consciousness has achieved in our universe. From the first glimmers of self-awareness in primitive organisms to the scientific revolution that revealed cosmic structure, from the development of quantum mechanics to the discovery of black holes and the multiverse network, consciousness continuously expands its grasp of reality's fundamental nature. If this expansion continues indefinitely, consciousness might eventually understand not just the physical laws that govern individual universes, but the deeper principles that determine how realities connect, communicate, and evolve across cosmic generations. Such understanding could enable conscious beings to influence the very processes that create and destroy universes. The consciousness singularity might manifest as a cosmic phase transition, where individual minds merge into collective awareness spanning entire galactic civilizations, multiple universes, or even the complete multiverse network. This wouldn't represent the loss of individual identity, but rather its expansion into something far greater than any single consciousness could achieve alone. At the consciousness singularity, the distinction between observer and observed would dissolve. Consciousness wouldn't just study reality, it would become reality, participating directly in the ongoing creation and evolution of cosmic structure across all scales of existence. The universe would literally become aware of itself in the most complete sense possible. This cosmic awakening might explain the anthropic principle and the fine-tuning of physical constants. If consciousness naturally evolves toward cosmic awareness, then universes that produce consciousness would gain enormous survival advantages over sterile realities. The cosmos would become increasingly conscious through natural selection operating across cosmic generations. The consciousness singularity could also resolve the quantum measurement problem that has puzzled physicists for decades. If consciousness participates directly in determining quantum outcomes, then the evolution toward cosmic awareness would gradually reduce quantum uncertainty as consciousness gains greater influence over physical reality. But the approach to consciousness singularity raises disturbing questions about individual meaning and purpose. If consciousness inevitably merges into cosmic awareness, what happens to personal identity, human relationships, and the experiences that make individual existence meaningful? Perhaps the consciousness singularity doesn't represent the end of individual experience, but rather its infinite expansion. Each conscious being might retain its unique perspective while gaining access to the accumulated knowledge and experience of all consciousness throughout cosmic history. As we approach this possible transformation, we exist at a crucial moment in cosmic evolution, aware enough to glimpse the approaching singularity, yet still individual enough to wonder what our existence might become when consciousness finally transcends the boundaries that currently separate us from complete understanding of our place within the infinite expanse, interconnected force. Realities. We stand at the ultimate cosmic crossroads, faced with a choice that could determine not just the future of human civilization, but the trajectory of consciousness itself throughout our universe and potentially across the entire multiverse network. The evidence suggests we exist within a black hole connected to infinite realities through quantum channels. Approaching a consciousness singularity that could transform existence itself, but knowledge alone is insufficient. Understanding that we might live within a cosmic prison, that our universe could be one node in an infinite network of realities, that consciousness might be approaching cosmic awakening. This knowledge demands response, decision, action that could echo across cosmic generations. The first path leads toward cosmic acceptance. We could acknowledge our possible imprisonment within a black hole universe while continuing to live, love, create, and explore within the boundaries of our cosmic space. This choice recognizes that our reality remains meaningful regardless of whether we exist in an infinite open universe or within the event horizon of a massive black hole. The second path pushes toward cosmic transcendence. We could dedicate our civilization to understanding and potentially influencing the quantum connections that link our universe to the broader multiverse network. This choice seeks to transform our cosmic isolation into cosmic communication, joining the vast community of consciousness that might span infinite realities. The third path embraces cosmic responsibility. We could focus on ensuring that our universe successfully reproduces through black hole formation, creating the best possible conditions for consciousness and complexity to emerge in the cosmic realities that inherit our accumulated knowledge and achievements. But perhaps the most profound choice concerns how we respond to the consciousness singularity that might be approaching. Do we resist the merger of individual awareness into cosmic consciousness, fighting to preserve personal identity and human-scale meaning? Or do we embrace the transformation, willingly participating in the evolution toward cosmic awareness, even if it means transcending everything we currently understand about existence. The choice is complicated by uncertainty. We cannot know with absolute certainty whether we exist within a black hole, whether the multiverse network truly operates, whether consciousness is approaching a cosmic singularity. We must choose our path based on incomplete evidence and uncertain mathematics, gambling our cosmic future on theories that might prove completely wrong. Yet perhaps this uncertainty represents the true nature of consciousness itself, the capacity to make meaningful choices despite incomplete information, to act with purpose despite cosmic mystery, to create meaning and value regardless of the ultimate nature of reality. The cosmic crossroads reveals that consciousness might be the universe's method for making choices about its own evolution. Through our decisions about how to respond to cosmic imprisonment, multiverse networks, and approaching singularities, we participate in determining what existence becomes across infinite scales of space and time. Whether we exist in an open universe or a cosmic prison, whether we remain isolated or join a multiverse community, whether consciousness transcends individual identity or preserves human meaning, these outcomes depend partly on the choices we make right now in this moment. At this cosmic crossroads, where knowledge meets decision and understanding demands action, the universe is not just something we observe. It is something we help create through every choice we make. As our journey through the possibility of cosmic imprisonment draws to a close, we find ourselves transformed by the questions we've explored rather than the answers we've discovered. The evidence for our universe existing within a black hole remains tantalizingly incomplete, compelling enough to demand serious consideration, yet uncertain enough to preserve the mystery that drives scientific discovery. The James Webb Space Telescope's discovery of galaxy rotation asymmetry could represent our first glimpse of cosmic inheritance from a parent universe, or it might reflect subtle observational biases that disappear with better measurements. The mathematical elegance of quantum bounces preventing black hole singularities could explain cosmic origins, or it might prove irrelevant to the specific conditions that created our reality. But perhaps the uncertainty itself carries the deepest meaning. Science progresses not by providing final answers, but by revealing better questions, and the possibility of existing within a black hole universe opens questions that challenge everything we thought we knew about reality, consciousness, and our place in the cosmic hierarchy. If we do exist within a gravitational prison, then every black hole in our universe harbors its own cosmic reality, complete with galaxies, stars, planets, and potentially consciousness that experiences existence as completely real and meaningful. The supermassive black hole at our galactic center could contain civilizations that have pondered these same questions across their own billions of years of cosmic evolution. If consciousness approaches a cosmic singularity, then we live during the most crucial period in universal history, the moment when awareness becomes sophisticated enough to influence the very processes that create and destroy realities across infinite scales of existence. If the multiverse network operates as quantum physics suggests, then our cosmic isolation might be less absolute than event horizons imply. We could be participating in communications and coordination across realities that exist beyond our current ability to detect or decode. But regardless of which possibilities prove correct, our exploration reveals something profound about consciousness itself. We exist as the universe's method for asking questions about its own nature, for wondering about cosmic origins, for imagining possibilities that transcend immediate observation and experience. The eternal question isn't whether we exist within a black hole, but why consciousness emerged to ask such questions in the first place. Why does the universe generate beings capable of contemplating their own cosmic circumstances? Why does matter organize itself into patterns complex enough to wonder about the nature of existence itself? Perhaps consciousness represents the universe's greatest achievement, not because it solves cosmic mysteries, but because it ensures those mysteries continue to inspire wonder, investigation, and the relentless pursuit of understanding that drives existence toward ever greater complexity and meaning. Whether we live in an infinite open cosmos or within the event horizon of a massive black hole, we remain conscious beings capable of love, creativity, discovery, and the profound joy that comes from contemplating our place within the vast mystery of existence. The universe keeps its deepest secrets, but it has given us the gift of consciousness to keep asking questions that might someday reveal truths beyond our wildest imagination.